In today's videos, we'll look at digitization, power and noise. Learning outcomes. You should understand the principles of digitizations and the techniques used, which is analog to digital conversion and digital to analog conversion. We'll look at voltage regulation. So you should understand the principles behind that. Have an appreciation of battery technology. And then we will finish with having a look at some good design practices when making circuits. So the first video will be on digitization. When we have a mechatronic system, we will have signals going into that system, and most of these will be analog. What we will need to do is convert this analog signal into a digital signal that the microcontroller or computer can then utilize, and then ultimately that will be transferred back to an analog signal, which will then be used to power actuators. The process is known as analog to digital conversion, ADC, and digital to analog conversion. When you digitize, it involves digitization in two axes. You digitize with respect to time, so you take points at discrete time intervals, but these points are also quantized in value, so you do not get a continuous signal. These will be in step format depending on the level of digitization. When we digitize, the signal will become a binary number. So depending on how many bits you have, that then determines how many levels of digitization you have. So for an 8-bit digitization, 2 to the n is 256. So you will have 256 different levels of value to represent that analog signal. For the digitizing process, you specify 3 different parameters. You need to know the range that you'll be digitizing over. So this is typically 0 to 10 volts, or in the case of the Arduino, 0 to 5 volts. The resolution, so that is the smallest increment in input you can measure. And then the speed, so how fast or how many samples you need to take per second. The resolution is determined by the number of bits you're digitizing to, and is defined by the range over 2 to the n. So for example, if we had a range that we wanted to measure between plus and minus 10 volts, so that is a range of 20 volts we want to measure over, and we want to measure to a resolution of 0.5 millivolt, then if we apply this equation here, rearranged, then the number of bits for our digitization has to exceed V range over resolution. If we work that out, in this case it is 40,000, and therefore n comes out to be a value of has to be greater than 15.28. So to obtain a 0.5 millivolt resolution in a 20 volt range input, we will need 16 bits in the digitization process. The other important aspect to consider when sampling is the speed that we sample at. The Nyquist sampling theorem states that sampling of a signal must be done at twice the highest frequency present. Or in other words, for every wave, so if we have an oscillating signal coming in at a certain frequency, for each wave that comes in, we have to measure 2 sample points. The best way to explain this is to work through an example. So say we have a signal coming in at 27.8 kilohertz. That corresponds to a wavelength of 36 microseconds. And what we're going to do is sample this every 1 microsecond. So we're going to be taking 36 measurements per oscillation, and this corresponds to a sampling frequency of 1 megahertz. So our sampling frequency is a lot more than twice our actual frequency. So this is our signal coming in, this solid black line, and the points on this curve represent us sampling every microsecond, or at a 1 megahertz sampling frequency. You can see the points. If you just look at the points, then we can quite easily reconstruct this wave from them points. So it's a good representation of the signal coming in. What we're going to do now is reduce our sampling frequency to 55.6 kilohertz. So this is now twice our actual frequency. So we've got an actual frequency of 27.8 kilohertz of our signal. Our Nyquist says you must sample the signal at twice this frequency, and therefore we're at the Nyquist limit if we're sampling at 55.6. If we do that, what we do is we take a measurement here, a measurement here, a measurement here, here, etc. So we still can reconstruct the wave from that, but only just. Now you could argue we might not actually sample at them exact points in time. We might sample here, and here, and here, and here. If we reconstruct the wave from that, we would get something like this. So it's not quite the original signal. It's lower in amplitude and there's a phase shift. However, it is still the frequency we're looking for. So in that respect, we still have measured that frequency. We'll now say we'll reduce the sampling to an even slower rate. So if we sample at 54 microseconds, or take one sample every 54 microseconds, we'll get a point here, a point here, a point here, a point here. If we reconstruct that wave, it actually looks like this dotted line. So now you can see the frequency, or how we imagine that frequency to be, is a lot lower than the actual frequency coming in. So we've got a false representation of the actual signal. This effect's known as aliasing. And what it means is if you do not sample fast enough, then the frequencies coming in appear to be at a different frequency to what they actually are. So it's important that you sample at a high enough frequency to capture that full wave coming in. So there's two options to do that. The first option is you sample at a fast enough frequency. Now remember I said that if you don't sample fast enough, frequencies appear lower than they actually are. So the consequence of that is if you want to measure this frequency here, but you've also got some noise in the signal, which is here at this frequency, you have to capture all of that data in order to eliminate the noise. So you have to take your highest frequency component in a signal, double that frequency to here, and then sample above that, so you capture all the information. If you sample twice, at least twice of this, but not twice of this, then this frequency will still be in your signal, but appear at a lower frequency. So the situation can get very confusing. So one option is to just see what any frequencies are in your signal, pick the highest frequency, and sample it at least twice that frequency. The downside, or the two downsides to this, is having to sample at a very fast frequency can be very expensive. The faster the digitizer, the more expensive it is. And secondly, you're paying extra for what is noise essentially up here. You don't care about any of this. This is all that you want, this signal here. So it'd be better if you can just measure this and eliminate anything here. So we have discussed a circuit to do that, and that is known as a low pass filter. And if you low pass filter here, you're just keeping your frequency of interest, you're eliminating everything up here, and therefore the Nyquist limit will be twice this cutoff frequency of your filter, which is here. So sampling a bit more than that is here. So therefore you've eliminated the noise, and you're still sampling at an adequate enough frequency. However, it's a lot less than in the case when there's noise present. So it'll be a cheaper solution. So this is just a low pass filter, but when it's used in an application such as this, it is known as an anti-aliasing filter. And all it's doing is removing the high frequency components. The term aliasing means when you don't sample quickly enough and these frequencies appear at a lower frequency. So that is the effect of aliasing. So anti-aliasing removes that effect. As an example, let us consider we wish to digitize a signal at 10 kHz, and we have got noise at 250 kHz, 400 kHz and 1 MHz. If we wish to sample all of that, we would need to do sampling of at least 2 MHz, which would be expensive. So instead, we'll use an anti-aliasing filter, which in this case, we will just use a simple passive low pass filter, where we know the 3 dB point of that filter is given by the corresponding resistor and capacitor values. So our Nyquist limit says we have to sample at least twice that 10 kHz. So we need something greater than 20 kHz. So something like 100 kHz, that's going to give us 10 points per wave or per oscillation. So that should be a fairly good representation of the signal. And then we want a filter that will allow 10 kHz through, but remove everything above 250 kHz. So we can set our 3 dB point at, say, for example, 50 kHz. And that will keep our frequency components we want and remove anything we don't want. We can put our 50 kHz into our equation for low pass filter, and we can pick resistor and capacitor values to satisfy that equation. So that is one possible solution to that problem. The process of capturing data is called data acquisition. So we need our analog to digital conversion stage, but there's also several other stages involved. The first one of these may be a multiplexer. This is optional. What a multiplexer does is reads in several signals, but only passes one signal through onto the digitization process. So this has the advantage that if you want to digitize several signals, you only need one digitizer to do this. The downside is because the digitizer can only digitize one signal at a time, then this is quite a slow process if you have got a lot of signals to digitize. Just before the actual analog to digital converter, you have a sample and hold circuit, which looks like this. This is important because you do not want the value to change while you are digitizing it. So you have to hold that value at a constant level. The circuit is fairly simple. All you have is a switch. So you close this switch, and whatever the input voltage is, charges this capacitor up. So this capacitor will be charged up to a voltage of Vn. When you open the switch, the capacitor then holds that value. So it doesn't matter if this input voltage changes at this point, this V in value is held constant at this capacitor. Now we don't want this value to discharge, or this capacitor to discharge. So what we have is the voltage follower arrangement here. So this is a unity gain non-inverting amplifier arrangement. Because this has a high input impedance, then you do not get any current flowing, so you're not discharging the capacitor. However, because it's a unity gain amplifier, the output here is going to be V in as well. So this is held constant, this voltage V in, until the digitization process is complete. And then when the next signal is wanted, switch is closed to put a new value on that capacitor. We will look at the analog to digital conversion next, but once that is complete, the answer then goes to a data register, and this is held, the value is held in this data register until it's read by your computer program. There's a set of control and status registers to control all these different processes. In terms of the analog to digital converter, we have lots of different options. We'll have a look at two in this video. The successive approximation, which is what the Arduino uses, and also the flash. But there are other options available. The successive approximation analog to digital converter works as follows. You have a storage register here, which initially starts off as all zeros. When there's a clock pulse, it changes the most significant bit to a value of 1. This value in here, so that's a 1000, is then sent to a digital to analog converter, so this digital value is converted to an analog signal and sent to a comparator. This value is then compared to your input signal. If the input signal is smaller than this value from the DAC, then it means this value is too high, and therefore this 1 gets changed back to a 0. If, on the other hand, the analog signal is greater than this output from the DAC, then it means the DAC value is currently too small, and therefore we keep this 1 in this place. When the next clock pulse comes in, we change the next bit to a 1 and do the same process. If this value is too high compared to the analog signal, it gets changed back to a 0. If it is lower than the input, then it stays as a 1. We can continue this process through each of these bits till we get to the last bit. So this is how that process works. You continually just setting bit values and then comparing the analog equivalent of that to the input voltage to get your digitization process. It is a cheaper method of doing digitization, but it's also slow because you're having to just check one bit at a time. A faster way of doing it is a flash ADC. And the idea for flash ADC is fairly straightforward. You have a reference voltage level here. So we can say that is, for example, we can say there's 3 volts there. If this is ground here, we have resistors here, so we've got a potential divider circuit, so we're going to get step down in voltages. So if it's 3 volts at this point, it's going to be 2 volts at this point and 1 volt at this point. Our reference signal comes in here, and then this is compared to the different voltage levels. So say, for example, that is 1.5 volts coming in there. So in this comparison, this 3 volts is greater, so this will be a negative output, a low output. On this comparator, you're comparing 1.5 volts against 2 volts, so it'll be negative. On here, so if that is positive and that is negative, that'll be negative output. In this case, you're comparing 1.5 to 1, so that'll be a positive and a positive here. So you can see the input signal is just compared to a series of voltage levels. Your output isn't actually a digital value at the minute, it's just a series of comparisons. So at some point, the reference voltage is greater, and then after that, the input voltage is greater. To convert that to a digital value, you then use a series of logic gates. So here's an example of what we could do. We could use a series of exclusive OR gates on here. And if you imagine, so these are essentially so logic circuits. So if we have, say, false on that one, and false on that one, and false, excuse me, I'll just go back a bit. So if we have false on that one, false on that one, so that would be a negative output, and then true, 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 true. So where false would be your negative output and true would be your positive output. So that is false there as well, it's earth. So if that's exclusive OR, then it means the inputs have to be different for you to get an output. So you get a 0 output on this one, a 0 output on that one. This has got a false and a true going in, so that would be a true, so that would be a 1. This is true and true, so that would be 0. So it'd be 0 on all them. So in this case, it would only be this one line that is activated, and this line connects to here and here. And therefore your output corresponding to this position would be 1, 0, 1, which equals 5 in this case. So it is a very fast way of digitizing, but it's also expensive due to the number of components you need. When you're using an ADC, it's a good idea to have this interface circuitry. So this serves a few purposes. Firstly, it acts as an anti-aliasing filter. So you have got your low pass filter here, R and C. So that will get rid of any high frequency noise components and hence any aliasing that might happen. It prevents the input voltage going out of range and so potentially damaging the converter. So you have two diodes here, this one and this one. So if these diodes were perfect, then if this voltage goes above 5 volts, you will get current flowing up there and therefore reduce this voltage to the 5 volt level. Alternatively, if this voltage goes below ground, so say it goes to -1 volt, you'll get voltage or current flowing here from ground up to neutralize that and bring it back to ground level. You do get a voltage drop across a diode of about 0.3, so it doesn't limit it to exactly 0 to 5 volts, but thereabouts. So typically it would limit it to dropping no lower than -0.3 and no greater than 5.3. So it does protect your converter. The last point is if you're multiplexing in your digitizer. And the trouble with multiplexing is you're switching channels here. So you might have switched from this channel onto this one. When you switched onto this channel, the sample and hold circuit here will hold that voltage. And if this capacitor is relatively large, then when you switch to the new voltage, there might be enough charge on that to actually influence the voltage reading you have coming in. So to get around that, this capacitor that's used as your anti-aliasing filter is also forming a parallel capacitance with this internal capacitor. And provided this one is relatively large, this capacitor is relatively large compared to this internal capacitor, then any voltage that might be present on there when this multiplexer switches has little effect on the overall voltage at this point because this capacitor is dominating. The other process we need to consider is digital to analog conversion. So we'll have a digital value in our microcontroller and we need to produce an analog signal out of this. We've got a resolution limit on the output given by the range of our output. So for example, it might be 0 to 10 volts and the number of bits that we're using for this process. So as an example, if we have, say, a 10 volt output range and we're using 8 bits in this process, then 10 divided by 2 to the 8 gives us 39 millivolts. So we kind of get a continuous output signal from this process. In this case, our output is limited to steps of 39 millivolts. When we do this process, we first have to hold the digital number in this latch. And we need to do this because as we are writing values to this register, then while we're writing values, we might inadvertently have the conversion process do an analog output of these values as they're being written, so they'll constantly fluctuate. So the process involves writing the value or writing all the different bits you need into this register, and then once that process is complete, that digital value is then sent to the conversion process. We have covered the circuits we need to actually perform this process, and it is the summing amplifier circuit. So if you remember back to Monday, then we had a summing amplifier arrangement where we could have different voltage levels coming on the input, and then we add these together with the non-inverting amplifier arrangement. For the summing amplifier, we've just got one reference voltage coming in, but then we weight these according to different resistor values. So it's exactly the same as the summing amplifier, except now we've only got one input voltage and various resistor values as the input resistor. And these are activated by electronic switches just prior to that. So if our digital number is 1101, then we'd switch this switch on, this switch on, this one is off, we'll leave this open, and then we'd switch this one on. And then the output would be a sum of these three components. The slight problem with this scenario is if you look at the transfer function, it comes out to be this, and although there's nothing wrong with that, there is a large variation in resistor values. Now resistors are typically about 1% accurate. So if you look at the example here for a 12-bit conversion process, the difference between the resistance you need for the least significant bit and the resistor you need for the most significant bit is a factor of over 2000. So any error in the least significant bit resistor far outweighs the actual value in the most significant bit resistor. So the problem with this approach is you just cannot get resistors with an accurate enough resistance value to make this circuit viable. There is an equivalent circuit you can use, which is this one, which is an R2R ladder DAC. This circuit is equivalent to this circuit, so it's, in terms of operational principle, it's exactly the same. However, now you've only got two resistor values, R and 2R, so it's a lot easier to match resistances. In terms of the transfer function for this circuit, and to prove it is the same as the other circuit, that is an exercise for you to do for today. So I'll leave that for you. Another option for a digital to analog converter is this string DAC. This is similar to the flash analog to digital converter, in which you have essentially a series of resistors providing a range of voltage levels at these different points, and then you have a series of switches for each bit of your digital value, and then these activate these switches accordingly to dial up the right value you want for your output. The advantage of this circuit is that because these values will change successively, then even if one of the resistor values is slightly wrong, you're still going to get a sequential decrease in values. So the actual voltage levels at each point should be fairly accurate. The final digital to analog conversion I want to consider is pulse width modulation. And this is the technique the Arduino uses. So if you remember, in the instrumentation and drives module, we drove the motors with a pulse width modulation signal. And essentially what you're doing is you're switching a digital signal on and off, and assuming the response of what you're driving is relatively slow, then all that device sees is the average of this signal. So if the duty cycle is low, so in this case it's going to be off more than it's on in the top view, then the average voltage or the DC level is going to be quite low. When it's a 50% duty cycle, the average level or the DC level is going to be at the halfway value, and when it's mostly on, it's going to be high. So by switching a digital signal on and off with whatever duty cycle is appropriate, you can get an equivalent analog signal out. But that's provided the switching of this switching is fast compared to the response of the system. You could pass this signal through a low pass filter, and that effectively just keeps the DC component and removes the high frequency components, and therefore you would just get this average DC level coming out. So that concludes our discussion on digital to analog conversion and analog to digital conversion. In the next video, we'll look at voltage regulators.